The next thing that so we have seen what you call a fair amount of theory. Now the question is why is this all this stuff even useful, right? And to kind of draw your attention to that, I am going to take a few examples. The first example I am going to talk about is rather what we are going to talk about is why is all this useful, right? And so there are as I said, there are many mixed signal circuits which are time varying, and in all these circuits it is often a good trick to know to be able to analyze them with a lot of simplicity. For instance, the first thing that I am going to talk about is chopped amplifiers. And before I get into the actual details, let me try and explain why chopping came about or is needed in the first place. So, it turns out that there are a lot of applications where the signals that are processed or amplified are very low frequency signals. Examples being signals that you acquire from the human body, right, like ECG, EKG, whatever, they are all very slowly varying signals, right. If you were trying to measure very small amount of weight, for instance, in a precision balance, for instance, this is mostly done using some kind of Wheatstone bridge kind of sensors. You have strain gauges, and then you are trying to amplify a very small difference in voltage, and of course, this voltage is a DC voltage and needs to be amplified. And the amplifier that you use, right, let us say it has got a gain of A, and it turns out that almost all amplifiers will have, in fact all amplifiers will have some what is called DC offset. Okay. So, this Vn is an input referred voltage which is got DC offset, plus it also turns out that there is something called flicker noise. So, if you look at the spectral density of the equivalent input referred noise voltage, it turns out that it will have a shape like this, right. So, this is SVN of f, and this is frequency, and it turns out that this will keep going like this. Remember from our earlier studies, we kind of expect that we always expect to see thermal noise. So, this is thermal noise, but in addition there is this 1 over f or flicker noise. Okay. And it turns out that our understanding of the physics of flicker noise is, I think there is still a lot of work going on in that area, but as engineers we have to understand that this is something that one has to live with. It is not something that one can get away with. The only way to reduce this flicker noise apparently is to make the process cleaner and cleaner. In MOSFETs, it turns out the flicker noise is because of trapping of carriers in the channel at the interface between the oxide and the silicon, and at any rate the only way to fix this or reduce the spectral density of this flicker noise is to have much larger, is to have a much cleaner manufacturing process, which is very expensive. You can also kind of reduce it by increasing the area of the MOSFET, right, and the problem with that is that speed becomes compromised, and to reduce flicker noise the flicker noise spectral density by a factor of 10, it turns out that you have to make the area of the device 100 times larger, right. So, that is a losing battle. And so, why is this flicker noise problematic? Well, if your signal if this is your signal content, right, if this is the desired signal, then as you can see, well, the what matters, the noise that matters is not the thermal noise, but the flicker noise, because in the signal band the it is dominant, right, and it can be many orders of magnitude larger than the desired signal, right. So, this is a serious problem, right, and there seems to be no clean, within quotes, device level solution to this, other than saying that, well, I need a much better device, okay, which might be A, maybe too expensive, B, it might be it might simply not be possible, right. So, you need what you call a more system level approach to be able to mitigate the effect of flicker noise, right. Now, what do you do? So, the idea is the following. Well, you know that it is only low frequency, it is only the low frequency portion of the input referred noise of the amplifier is degraded by flicker noise. The higher frequency part, namely this area here, is basically only thermal noise. So, the idea behind one approach to avoid this flicker noise problem altogether is to say, I will take the input signal, translate it to high frequency, where we know that the input referred noise of the amplifier is only white. You go there and then you amplify the modulated signal at that at high frequency. I mean, you take the input signal, you modulate it to a high frequency, high enough that you know that the amplifier's noise is only thermal at that point, and you amplify it. The amplified signal will still be at this high frequency, and then you can demodulate the amplified signal back to baseband, right. So, that is the basic idea, and so modulation is as you all know, is simply multiplying with a sine wave. So, for example, I am going to assume that this is cos 2 pi f naught t. I will call this f c t for a good reason, right, and I will multiply the output also by cos 2 pi f c t, all right, and so this is, so let us see what happens in this case. I mean, one thing to observe is that what kind of, if I now put all of this in a box, what kind of system is this? It is an LPTV system, right. So, even though the amplifier itself is time invariant, because of the multiplication, this becomes an LPTV system. All right. So, let us see first of all how this this stuff works, right. So, if this is x of t, let us assume, I want to redraw this. So, this is x of t, the input, f c is called the chopping frequency, and this is the input referred noise of the amplifier, or actually this will be a, I mean if you are drawing the signal flow graph, this will be a summation, this is V n, this is going to be amplified by gain A, this is cos 2 pi f c t, and this is y of t. All right. So, let us see what the spectra are at various points. So, what comment can we make about the spectrum there? Let us only draw the positive side, or maybe we can draw the negative side also. So, let us say this is x of t, it is baseband, right, with some bandwidth minus b to plus b. So, what happens when you multiply it by cos 2 pi f c t? It gets frequency translated to f plus f c and f minus f c. Yeah, so basically let me, so this is, I think I should draw this more to scale, hold on. This is b and this is minus b, this is, let us assume that this is f c, this is f c plus b, f c minus b, and similarly this is f minus f c, and you have the same thing, right. Okay. So, the next thing is what happens? Well, we are adding, so at this is the spectrum at A, all right. What will be the spectrum at A hat? You have to add DC offset and flicker noise. So, let us assume that we add flicker noise now. So, this is 1 over f noise, all right. So, this is the spectrum at A hat. Now, what does the amplifier do? Well, the amplifier will amplify everything that it sees. So, right, that goes there. This is amplified flicker noise, and this is the amplified signal. This is B, this is what you see at B. Now, what happens? This is amplified signal. All right, and now if you multiply this by cos 2 pi f c t, what do you think will happen? This will get translated to the left and to the right. So, when it gets translated to the left, so let us say this is y of t. So, we need to worry about, and by the way, if this was x of f, the amplitude of this is half and this is also half, and that is because cos is 1/2 of e to the j 2 pi f c, and yeah. So, this will be a by 2, is a by 2, correct. And now, when you translate this to the left, you basically will get a by 4, right, and you will get another baseband tone when you translate it to the right, which is also a by 4. So, when you add the two together, you get a by 2. You will get a tone, you will get you get something at 2 f c. That is 1 second, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is you will get something at 2 f c, right. So, this is 2 f c, and you will get something else at so this is the spectrum at y. So, this is minus 2 f c, and this is b, this is minus b, all right. But we have forgotten one thing, the flicker noise is also going to get translated. So, what is going to happen? You will see something at f c, right, and you will see something at minus f c. So, so this is minus f c and this is plus f c, all right. So, we have a whole, I mean this is our desired signal, but we have a whole bunch of undesired components. So, all this is something that you do not want, right. Fortunately, they are at either at a frequency f c or much higher. So, what do you think you will do? We can filter them out. So, what you want to do therefore is to put a low pass right. So, this is y of t and this is y hat of t. So, the y hat of t is take this and simply filter it with a low pass filter. So, this is minus b, this is b, and the gain is a by 2, all right. So, fortunately, as you can see, the even though the amplifier has got a lot of flicker noise, we have avoided the output does not contain any flicker noise component. Well, we have seen everything in the frequency domain. In the time domain, it's it's easy to kind of understand intuitively what's happening. Well, flicker noise is concentrated at low frequency. So, you can think of it as a slowly varying DC offset, right. So, if it's varying very, very slowly, correct, and the slowly is with respect to what? With respect to the chopping frequency, right. So, if the amplifier's input referred, I mean the flicker noise is evidently a very low frequency phenomenon, and you can think of it as an offset which is changing slowly with respect to frequency. The idea is that, well, if you process the signal with positive offset, right, and then for a little bit of time, and then with a negative offset for the next time slot, the offset has become positive and negative, and whereas and if you do the same thing at the output of the amplifier, right. So, in other words, intuitively what you can do is time slot A, you can process the right, and so if you put x of t, you get x of t minus VDC times A, in time slot B, you put x of t you flip the sign of the amplifier. I mean, you arrange things such that the effective offset has become minus DC, and that is easy to arrange, right. For instance, you could, I mean, you do not have to physically invert the amplifier, you could invert the input signal, right, and invert the output of the amplifier also. So, that effectively you get a negative DC. So, you basically get x of t plus VDC times A, right, and if you do this sufficiently fast and you average the two outputs, then you will be able to get x of t into A. So, that is the idea behind chopping, right. But because of the periodically time varying nature of the system, right, you can have a potential for, I mean, remember that our output frequency of interest is low frequency. That is, I mean, the frequency of our baseband signal resides here. That is where our that is the frequency range over which our baseband signal results resides, right. But because this is an LPTV system, there is a chance that other frequencies, this is LPTV at FC. So, we should in principle expect that all frequencies of the form output f plus L times FC will all can potentially alias to our desired output, right. So, the obvious question is first of all, what are all the frequencies that can alias? B, what is the strength with which what is the gain from those frequencies to this our desired output frequency, right. And we would also like to find what the actual transfer function is from, and what do you expect, I mean, what do we see before we do the math, right. A low frequency input V of n, what is happening to it at y? It is getting translated to Fc. So, we should expect that H0 from Vn to the output is actually 0, right, because if there is DC here, Vn to y of t it is 0, and therefore, Vn to y hat of t also it is 0, correct. We should expect the transfer function from Vn to y hat to be 0, because y hat is basically removing everything at Fc, right. So, in other words, we have multiple inputs, we have two inputs here actually, x of t and Vn, and we would like to find the transfer functions from, I mean, we would like to find what all components of Vn and x of t can potentially translate to low frequency or to DC at the output. Does it make sense, right? And therefore, this is going to be I mean, this is easily addressed by when you have multiple inputs as well as multiple frequencies, right. It must it makes a lot more sense to use the principle of interreciprocity or the adjoint, and we will do that in the next class.